Three, another beautiful day in Cambridge. We've been blessed this week, really, given what the weather's been like in the UK in recent weeks. Anyway, I'm delighted that we've got Rebecca Willett here again to talk to us. Over to you, Becca.
Great, thank you very much. It's a real pleasure to be here again. And I'm excited to tell you about some recent work that I've been doing with Garvesh Raskutti and his student Yuan Li on graph total variation regularization for inverse problems with highly correlated features or designs. So this is a problem that we started thinking about when we were talking with some psychologists and neuroscientists at the University of Wisconsin. And they are interested in the problem of neurodecoding. So what they might do is have a number of trials where in each trial they show a stimulus to a patient. And while the patient is looking at the stimulus, they record the neural activity in the patient, say using functional MRI or fMRI. And from that data, they would like to figure out what parts of the brain are encoding information about the stimulus. And then from that, be able to record someone's fMRI in the future and basically infer or predict what the stimulus originally was. So what we record would be something like the following. For each different stimulus, we would record the activity in each voxel in the brain, resulting in a number of different measurements. So if we have n different stimuli and p voxels in the brain, then you can think about this as a big n by p matrix of fMRI measurements. And we can think about the neural decoding problem as being a linear inverse problem, where now this matrix of fMRI measurements is my design matrix. So each row corresponds to a different trial, each column corresponds to a different voxel in the brain. And my response vector here would correspond to which stimulus was presented to the patient in each of the different trials. And what we'd like to do is find some weight vector that is going to basically allow us to make good predictions and figure out which voxels of the brain are doing this encoding. So we've got a weight for each one of the voxels that helps us predict the stimulus. And in general, we expect that this weight vector would be somewhat sparse because we don't think every part of the brain is being used to recognize that we're looking at a cat. So the question is how to solve this inverse problem. And this is something that in general has received a lot of study over the last several decades. But the problem that I want to focus on today is the situation in which the columns of this matrix are very highly correlated. So we're going to write this as y is equal to x beta plus epsilon. So y is our responses, x would be, for instance, our fMRI data, beta are these weights that we ultimately want to estimate, and epsilon is some noise. And the columns of x can be extremely highly correlated in many situations. So in the context of fMRI, for instance, often n would be on the order of 100 and p would be on the order of 100 or 10,000. So we've got 2 orders of magnitude difference in the side lengths of this matrix. But also there's physiological reasons. I mean, the way the brain works, you've got blood flow going to similar areas along similar tracks, and when we take fMRI measurements, we're measuring the blood oxygenation dependent level signal. And so there are physiological reasons why connected areas of the brain are going to have similar kinds of behaviors, resulting in high correlations in this matrix. And so the question is, what can we do to mitigate this challenge? So first, before I go into how we're going to mitigate it, let me explain in a little bit detail why it's a challenge. And we can see this in a very simple toy example where imagine we only have 2 voxels in the brain, and they're very highly correlated. And if our hypothesis is that only one voxel is really encoding information about the stimulus, and we want to choose which of those 2 it is, so basically we want to solve this inverse problem where our weight vector is very sparse, maybe 1 sparse, what we end up doing is selecting whichever one of the columns seems to be more highly correlated with our response vector, and this turns out to be just extremely sensitive to noise. So it's a very low power test. And so when you have high correlations in your data, it becomes very challenging to estimate what beta might be in certain scenarios. Yeah?
So if the columns are so highly correlated, can you still assume your beta is sparse?
Right, so we're going to actually end up assuming something a little bit different about beta. So it's not going to be completely dense. There's going to be some amount of sparsity. But as I mentioned in the title, we're going to end up doing some sort of total variation regularization that's a little bit different than pure sparsity. No.
In this experiment, can you just remind me what the sensing matrix is?
So each row corresponds to a different trial, like a different stimulus presented to the patient. And each column corresponds to a different voxel in the brain. So I would collect my fMRI data, and for that voxel I would get a time series of measurements as the patient is looking at the stimulus. And then the psychologists have models of what that curve should basically look like. And so they're doing some curve fitting to those time series and extracting a parameter. And so each element of my design matrix would be that parameter for different voxels in the brain. And that's a standard operating procedure for that kind of data. Okay, so despite the fact that we've got highly correlated columns and many more columns than rows, we also have some additional sort of side information in this setting. So technologies like tractography or diffusion MRI are separate sensing modalities that give us information about what these connections between different voxels in the brains are. So as you might expect, if we've got two voxels that are right next to each other, then they're likely to be connected. But there are also a large number of sort of long-range correlations across kind of distant locations in the brain that are just physically connected and presumably working jointly to encode different kinds of information. So we have highly correlated columns, but we also have a lot of information about what the nature of those correlations are and where they come from. And so what we'd like to ultimately do is to somehow leverage this information about these correlations to get more accurate performance. Okay, now this was a problem that I've been talking about in the context of fMRI, but it shows up in other applications as well. One of them that some of you might be familiar with is genome-wide association studies, or GWAS, where we might have a number of different people who each may or may not have some disease, and we'd like to figure out if there are certain genetic markers for that disease. And so you might have heard about this being very successful in the case of breast cancer, for instance. So for each patient or subject, we would record their SNPs, or their single nucleotide polymorphisms, and from that SNP data, we would like to infer which SNPs are good predictors of certain diseases. So again, we can formulate this as a linear inverse problem where we've got the disease state of our different subjects, and in each column we would have information about different SNPs in different locations along the genome. And again, there are physical reasons why we would expect the columns of this matrix to be highly correlated. So biologists have studied for decades things like genetic linkage or linkage disequilibrium, which describe how certain traits are not independently inherited from their parents, but rather there are certain traits that are more likely to be kind of co-inherited. And this has been quantified, and people have studied linkage disequilibrium to say exactly for different pairs of SNPs how likely they are to be co-inherited and therefore correspond to correlated columns in these inverse problems. So again, we've got this nice source of side information. Okay, one more kind of potential application that I haven't studied a lot, but you could imagine owning a company that you want to harvest all kinds of social media data from Facebook and predict who's going to respond to certain political ads. And hypothetically, we could call this company something like Cambridge Analytica. And so Cambridge Analytica goes and they say, which people are going to respond well to ads that feature puppies? And so for each person in our database, we record what words show up in their Facebook posts. And some people are posting about values and kids and children, and other people are posting about data and analysis and objectivity. And again, we'd like to figure out, well, which kinds of keywords are good predictors of how much you care about puppies in the context of political ads. So I'm not saying Sarah and Richard hate puppies, just they don't really say much to them about politics. And again, in this situation, there are strong correlations among the columns. So just because Ivanka talks about kids and Steve talks about children doesn't mean they're really talking about something different. And tools like Word2Vec and similar tools give us side information about the similarities or correlations among these columns. And again, we'd like to be able to somehow leverage that side information. Okay, so before I go into the approach that we've developed, I want to talk about just a couple of pieces of other works that have tried to handle strong correlations in these regression problems. So one piece of work is developed by my colleague Rob Nowak, who talked here yesterday, called the ordered weighted lasso. And first I'm just going to briefly describe the lasso because it'll give us a basis for comparison. So many of you know the lasso. We try to find a beta vector that's a good fit to the data and which is also sparse in terms of a small L1 norm. And geometrically, we can think about if we only had a two-dimensional beta, this red diamond corresponds to all the betas with a 1 norm less than some constant, say 1. And each ellipse here corresponds to a contour or a set of betas that are all somehow equally good fits to the data. And so what the lasso ends up doing is choosing the point or beta vector which is the best fit to the data within this ball. And that often ends up being a sparse vector. So what the order weighted lasso does in contrast to this is it says let's choose a different regularizer where we sort the elements in our beta matrix from biggest to smallest in terms of absolute value and apply a different weight to each one of them. And depending on how you choose the weights, you can do different things. One approach called Oscar, developed by Bondal and Reich in 2008, says that essentially the regularization function corresponds to a ball that's kind of more like this octagonal shape. And what happens is that when you again look at the beta vector that's the best fit to the data, so a point on one of these ellipses that first starts to touch this ball, you end up with higher probability on something in one of these sort of diagonal directions, which would have the two elements, beta 1 and beta 2, having the same value. So in other words, what this is doing is if you have highly correlated columns in your design matrix, and you were to use a regularizer like this, then you would be more likely to assign the weights for two highly correlated values the same amount of weight. So I can't tell whether column A or column B is more predictive, and so I'm going to assign them equal weights, and that happens somewhat naturally with this OWL framework. And we're going to see later that it works very nicely in a lot of simulations, but it does not have a natural mechanism for incorporating any of this side information that we have access to about the correlations among columns. It just has this sort of implicit adaptivity to these correlations. Now another approach developed in part by Sarah Vandegeer here is the cluster representative lasso. So what they do is they say, well, let's look at this design matrix that we're interested in, and we know that there's many different correlated columns. And so what I'm going to do is I'm going to cluster those columns, and I'm going to choose one representative column from each cluster. So instead of having 16 columns where I've got 4 clusters, I'm going to end up with a new matrix here with just 4 columns. And then I try to learn a weight for each one of those columns. And the idea is that all the columns in one of these clusters should have basically, again, the same weight. So this turns out to work especially well when there's very strong clustering among the different columns. And we'll see some examples of that later on when we look at some examples and simulations. And it also allows us to incorporate side information about correlations when we're doing this clustering. But when you have weaker clusters, it can be a little bit ambiguous about how to actually do this clustering, and you become a little bit more sensitive to noise. So the approach that we're going to consider today, like I said, is more of a graph-based approach. And again, this is motivated by our thinking about this fMRI application. So we assume that underlying everything, we've got some graph where the vertices correspond to our different covariates. So for instance, in fMRI, each vertex would correspond to a different voxel in the brain, and I need to assign a weight to each vertex, or a coefficient, a beta coefficient to each vertex. And this graph is going to tell us 2 things about our problem. the first thing it's going to tell us about our problem is something about how similar different pairs of weights or pairs of beta coefficients should be to one another. So if I've got two vertices in a graph which are very high, have a very high edge weight between them, then I would say, well, the corresponding beta coefficient vectors should be similar. So in the context of fMRI, I've got two voxels in the brain. They are highly connected to one another, and so I think they are working jointly to do some encoding, and so I should give them equal weight in my regression. In addition, I'm thinking that this graph is going to convey information about correlations among the covariates in my design matrix, or correlations among my columns. So a little bit more specifically, if we think of X as this design matrix, then we're going to, in our theory, assume that each row of this matrix X is going to be drawn from a Gaussian distribution with a covariance matrix sigma. And the sigma jk's, or the elements of this sigma matrix, are going to correspond to the edge weights in this graph. So if nodes A and B are have a very strong edge weight, then that would correspond to them having a high covariance in this covariance matrix. So now I've got a graph structure that's doing two things. One, it's conveying what this covariance matrix that dictates correlations among the columns of X's. And two, it's saying something about how similar different weights in my weight vector should be to one another. And so the question is, well, what do we do with this? So the regularizer that we are going to consider today, this graph total variation regularizer, is the following. So we're going to solve an optimization problem where the first term corresponds to the fit to the data. And now we're going to have three different regularization terms. And I'm going to talk at some length about what each of those is doing and why they're important. So the first one is summing over all pairs of voxels in the brain, or all pairs of covariates, and looking at the squared difference between them and multiplying that by a weight corresponding to this covariance. So if I've got two columns that are highly correlated, this sigma will be large, and I'm going to assign a bigger penalty if the corresponding beta weights are more different from one another. And I want to emphasize I can handle differences in signs here, but I'm just assuming everything's positive to make the notation simple in the talk. But our theory handles both positive and negative correlations. The second term is somewhat akin to the first, only instead of having this squared difference between the beta j's and beta k's, we have the absolute value. And so this is what's known in the graph signal processing community as graph total variation. It's also related to things like graph trend filtering by Ryan Tibshirani, and it comes in a number of other different names. And then finally, we've got a lasso regularizer. So this first regularizer, this Laplacian smoothness regularizer, is essentially reducing the ill-conditionedness associated with our design matrix X. And I'm going to be a little bit more explicit about how it does that soon. The second regularizer here, this total variation regularizer, is going to promote estimates that really are well aligned with our graph structure. So if we go back to our previous slide here, if I have betas that all have similar values here, then that's going to be well aligned with the graph structure that says that I think all of these nodes should have similar values. And then finally, we're going to use this lasso penalty to convey the fact that even though we're not going to be as sparse as a classical lasso estimate, we still think not every voxel is encoding something about what visual stimuli we're receiving, or that there's some degree of sparsity in our estimators. Yes?
Just for clarity, Rebecca, the sigma jk in the graph total variation penalty is not taking care of directly of the high correlation in the X. I mean, in other words, if you did not apply the Laplacian smoothness term, what would happen?
So yeah, I've got an answer for that. I think it'll be a little bit clearer later. But basically, imagine in X we had two columns that were perfectly correlated, then there's going to be no restricted eigenvalue condition, no restricted isometry property, and there's no way, you might be able to get good prediction errors, but there's no way you would ever be able to get a good estimate of beta without making some pretty strong assumptions. And so the role of this Laplacian smoothness regularizer is to basically mitigate that problem and give us a more or a better conditioned inverse problem. And I'll be very explicit about that in a little bit. Oh, yeah.
Sorry, so if you have two highly correlated x's, then this is going to actually push them to have the same beta?
It is. And that's, again, consistent with a lot of the other work in this vein where you're dealing with correlated designs.
But in your context, if you have two highly correlated x's and only one of them is significant, that means you got one of the betas wrong.
Yeah, that's right. So, I mean, I think there's a few ways of thinking about that. So for what we're doing with the theory that I'm describing, we are assuming that this graph structure provides an accurate prior on beta. So if I've got two edges that have a large edge, I mean two nodes that have a large edge weight between them, then they really should have similar values. And so the scenario that you're describing would be extremely unlikely according to our prior. But another way of thinking about this, and this is something that we don't have theory about, but which I'm pretty sure is true, is that we're basically, if you think about there being a true support set, we're not going to be able to identify it exactly because of these correlations, but this method should find a superset for it. So the true support should somehow be inside the support of our estimate. So if there's one voxel, so let me put it this way. If we go back, way back here, to this example, imagine just one of these columns is active, which is what you're asking about. We're going to identify both of them as being active. We're going to say there's really no way we can distinguish between the two of them, but at least we haven't thrown away something that's truly active. And so, I mean, I think that's the right way to think about it in the context of these applications. That we're at least we're just not getting rid of things that are truly important. And if you were doing some sort of, you know, sequential experimental design like you would with any kind of scientific method, then once you have this superset, you would say, okay, well, can I design an experiment to narrow this down even further? So again, that's not really the focus of our theoretical results, but I think that is sort of what you would really, the right way to think about it in the context of these applications. Okay. Okay, let me just introduce a little bit more notation. So we talked before about having this sigma, which corresponds to our covariance matrix for our design, but also sort of the weighted edge matrix for our graph. We can also write everything in terms of something called an edge incidence matrix gamma. So each row here corresponds to a different edge in our matrix. And so if I've got an edge between nodes A and B, then I have a row here, and the difference here is going to correspond to the covariance between these two elements. And so there's no real difference between the information encoded in here and the information encoded in here, but it's going to be a convenient way to write and simplify our estimator. And you might note that if you were to look at this edge incidence matrix transpose times itself, you just end up with the classical graph Laplacian. Okay, so we talked about this estimator here. It looked kind of long and complicated, but we can write everything very simply in terms of this edge incidence matrix gamma. So this sort of Laplacian smoothness can be written as gamma beta to the 2 norm squared, and this total variation is gamma beta 1 norm. Okay, so like I said, what we're really going after with these regularizers are estimates that are somehow well aligned with our underlying graph. So just to give you a little bit of intuition, if we had this sort of edge incidence matrix that's telling us which nodes are connected to which other nodes, and we had a beta vector, well, these are the numbers, but you could think about it pictorially like this. So these yellow circled nodes are the ones that are somehow active or have a large weight in this beta vector. We would say this is well aligned with the graph because similar valued nodes are also have large edge weights between them. And so this total variation regularizer would be small for this kind of signal. And in contrast, if we had a beta vector or a coefficient vector that had large weights on these yellow circled things, we would say this is not well aligned with the graph because we have things that are not strongly correlated that have very similar values, and other things that are highly correlated that have very dissimilar values, and so this regularizer would be large. So with this sort of scheme, we're ultimately seeking coefficient vectors that are well aligned with this underlying graph structure that, again, we think has physiological meaning in things like fMRI and real meaning in other applications. Do you have a question, Holger? Oh, okay. Okay, so before I go into the theory, I want to mention that there are several related ideas out there in the literature. So there's a wide variety of papers that have thought about this total variation or graph total variation or trend filtering kind of regularizer that we're discussing here. But many of those papers are focused on what I would call a denoising setting. So there's no X matrix, or the design matrix is simply the identity matrix, and they don't have the same kind of inverse problem. They're just trying to do some sort of smoothing or noise removal. And so there's a lot of good theory there that we leveraged in our analysis, but they're really addressing a very different problem. You might have also noticed that the regularizer, or the estimator that I'm describing, has something in common with the fused lasso or the edge lasso, where they also have this sort of total variation penalty and a lasso penalty. But the key distinction there is that when people look at these estimators, for the most part, they're assuming that whatever this graph is that we're using to form our regularizer is wholly independent of our design matrix X. So most of the theory there would assume that this design matrix X satisfies something like a restricted eigenvalue condition or a restricted isometry property, which is something that we cannot assume in the settings we're interested in. And again, Sarah recently looked at the smoothed lasso, where they had more of this Laplacian smoothing regularizer that we're leveraging here. But again, that analysis focused primarily on the case where this regularization matrix is somehow independent of the design matrix X. So the form of the estimator is similar to other things that have appeared in the literature, but what we're going to say theoretically is going to be quite different. Okay, so let me just try to do a little bit of algebraic manipulations to hopefully boil things down to something that looks a little bit more recognizable. So this is the estimator that we've been talking about with our three different regularization terms. And what I'm going to do is I'm going to combine terms. So I'm going to take these squared error terms, I'm going to write it as one squared error term, and I'm going to combine these L1 terms into one term here. So I can write everything in terms of a change of variables. So y tilde is y and 0, x tilde has x and gamma in it, and gamma tilde has gamma and the identity matrix in it. And now we can start to get a better sense of what's going on here. So once we write it in this form, we can say, okay, now I've got a linear inverse problem where my design matrix x tilde all of a sudden is better conditioned than my original X design matrix. And so that's one of the key roles of this Laplacian smoothing term, is that we end up having a data fit term that's a much better condition, that leads to a much better conditioned inverse problem than we originally had. And we also have sort of a simplified expression for our regularizer. Okay, now we can do a little bit more algebra here, and we can do a change of variables and say, well, instead of thinking about beta, let's think about a different variable theta, where theta times the pseudo-inverse of my regularization matrix gamma tilde is equal to beta. And I can just rewrite everything now in terms of theta. And once I do this, it starts to look a lot more like a classical lasso problem, and we've got all kinds of nice tools for analyzing this kind of estimator. But now we've got this funny looking matrix in here where we've got x tilde, which remember is the original design matrix X, stacked on top of our graph incidence matrix gamma, and the pseudo inverse of gamma tilde, which again has gamma and the identity matrix in it. And so in order to really understand what this estimator is doing, we have to think carefully about what this matrix is, what its form is, and what kinds of properties it has. So can we show, for instance, that this weird product satisfies the restricted eigenvalue condition? Okay, so that is in fact what we do. And so let me show you what comes out of that kind of analysis. So I have to make a couple of assumptions about our covariance matrix. This wouldn't work for an arbitrary covariance matrix. So in particular, we assume that the maximum eigenvalue of our covariance matrix is bounded. and that if we were to look at the absolute column sums of our covariance matrix, that these are bounded below. So we don't have any column of our covariance matrix that's all zeros, for instance. In addition, we acknowledge that in general we would not have access to exactly the true gamma covariance matrix sigma, but rather that we would have to estimate it from data. Maybe some side information, but nevertheless it's going to be an imperfect estimate. And so everything I said before about building and constructing these regularizers is based on some estimate sigma hat, not the true sigma. And we assume that the distance between sigma hat and sigma is not too big. And there's a wealth of literature on estimating covariance matrices under different settings that suggests that coming up with an estimator like this should be feasible. Okay, so given all of this, this is what we can prove. So, and I'm going to slowly unpack this. I know it looks messy. But basically we've got a parameter rho that I'm introducing, which is the maximum column norm of this pseudo-inverse of gamma tilde. And remember, when we did our little change of variable over here, the pseudo-inverse of gamma tilde suddenly showed up. And so we need to explain something about the role of that in our analysis. And once we have that maximum column norm, then we have a lower bound on how big our regularization parameter lambda 1 must be. And if that condition is satisfied, we've got this mean squared error. Okay, so let's unpack this. So first of all, let's think about this rho parameter here that corresponds to the max column norm of the pseudo-inverse of gamma tilde. This expression depends on the structure of the graph that we're really working with. So the size of vk corresponds to the number of nodes in the kth connected component of our graph. And mu k is going to be the smallest non-zero eigenvalue of the graph Laplacian for that kth connected component. And so this is where the structure or the geometry of our graph is really going to play a strong role in our performance bounds. So what I have here is somewhat generic, but we can specialize it to particular graph structures. And rho is what really allows us to see the differences between different graph structures and performance bounds. But rho, which is controlled by the geometry of our graph, shows up as controlling how big lambda 1 is, and lambda 1, of course, is controlling how big our mean squared error is. Okay? Secondly, I mentioned that others have considered this sort of total variation regularization in other contexts, especially denoising. So Hutter and Rigolet, a couple of years ago in particular, studied this problem in a denoising context. And they had a similar sort of quantity, only they looked at the pseudo-inverse of gamma. So they didn't have this gamma tilde that incorporated the identity matrix, which is coming from the fact that we've got this extra lasso regularization term. So they did just total variation, not total variation plus lasso. And as a result, they ended up with a value of rho that in many cases could be quite a bit bigger than the value of rho that we're able to achieve with our analysis. So by incorporating this lasso regularization term, we're able to get much smaller performance bounds in some settings. Okay. Next, let's look at the role of lambda TV. So this is how much weight we're applying to the total variation regularizer. And it's showing up in this weird place inside this value of rho, which in turn controls the value of lambda 1. And so in general, if you were to crank lambda TV up, you're going to make this rho smaller, which is in turn going to allow lambda 1 to get smaller. And we see in our performance bounds that we have lambda 1 and the product of lambda 1 and lambda TV. So we have this not so trivial trade-off between how much regularization we do on this total variation norm and how much sparsity regularization that we do. And you can really sort of turn this knob to get different rates of convergence with different graph structures. And so it turns out that you can, in some graph structures, make this lambda 1 much, much smaller than it would ever be able to be in a classical lasso setting and get much smaller errors. And again, we're going to look at some examples in just a minute. Let me unpack this a little bit further. we see that this lambda s times the measure of how well aligned our original signal is with the graph via the graph Laplacian shows up in terms of how big lambda 1 needs to be. Now, one thing you might ask is, well, why are you doing this Laplacian smoothing as opposed to doing classical elastic net kind of smoothing? And the answer to that is that the Laplacian smoothing that we're doing allows, again, this term to be much smaller than it would be if we had used an elastic net kind of estimator. Okay, I think a couple more insights. Generally, our bounds are all smaller whenever beta star is better aligned with our graph, which of course makes complete sense, right? The better beta star corresponds to our prior assumptions, the better off we're going to be. And then finally, Sarah, I think, put it really nicely in her paper on the smooth lasso. This parameter lambda s, which is showing up both in sort of a restricted eigenvalue condition like way in our error bound and in terms of a bound on how big lambda 1 is, essentially allows us to control the trade-off between how well we can solve problems that lasso can't solve, so how well we can address the ill-conditionedness of our problem, and how well or how quick our rate of convergence is. Okay, so let me show you some examples. So the first toy example we're going to look at is a block, or I guess we've got k different connected components, and each connected component is a complete graph or a complete subgraph. So the columns of x within each block are very highly correlated, and between blocks there's almost no correlations. So with our graph TV estimator, we get a mean squared error in this using what I was just describing to you that scales like b, the number of different blocks, log p over n. And in contrast, if you were to look at a classical lasso analysis, this error bound would scale like the total number of non-zeros times log p over n. So if all of the betas corresponding to one block were all somehow active, so if this corresponded to one region of the brain and every voxel in that region of the brain was encoding information, then our error for the lasso would correspond to how big that block is, whereas the error for our graph total variation would just scale with 1 because there's only one block really active. So we can get significantly lower error bounds in this kind of setting. So to give you a little bit more of an empirical flavor of what these different estimators we've been talking about are doing, here's an example where we constructed exactly the kind of graph that I was describing. There are 280 columns and 100 different rows, and the support of beta is 84. So there's 84 somehow non-zeros in our true estimate. But of the different blocks, only 6 out of the 20 are active or have non-zero support. Okay, so if we were to somehow just write all of this in lexicographical order, this would be our true beta that we want to estimate. And these are the estimates we get with graph total variation, and I'll tell you the difference between them in just a second. This is the estimate that you would get with regular old lasso, which we would not expect to do well because this really is not particularly sparse. This is what you get with the order-weighted lasso, this thing that adapts to correlations without any kind of side information. And this is what you would get with the cluster representative lasso. Now, with the graph TV, I've got two different estimates here, where it just says graph TV esti. That corresponds to using the design matrix to compute the this graph using the sample covariance matrix. Whereas INDEP here corresponds to having an independent sample that we can use to get an even more accurate estimate of this covariance matrix sigma. So this corresponds to the case where we really have a good independent source of side information. And so what we can see is that with the cluster representative lasso, for instance, when we have enough data to have a really good clustering, it does super. But when the clustering is less good initially, it's hard to recover from that. And I would say that the reason that the graph TV is not quite as sensitive to that effect is that when we are implicitly doing clustering within this graph total variation framework, we're using not only the columns of X, but also the responses Y. So the responses Y are kind of informing where we think there should be somehow breakpoints in the signal or where there should be clusters of beta. And that information about y is not used in a method like this cluster representative lasso.
Can you repeat
Yeah.
how the information of the y's are entered in this estimator?
So I'm being a little bit hand wavy here, but what I
don't
mean
see it from, yeah.
What I mean is that when we look at this estimator, I'm not doing any explicit clustering. I'm just saying find an estimator that has a small total variation relative to this graph. And so if that graph has these sort of blocks, these complete blocks, then I should somehow find a beta that's supported on a small number of blocks. But in order to find that beta, I'm using the graph structure and I'm using y simultaneously. Whereas the cluster representative lasso is a two-stage approach where first I do the clustering, totally ignoring y, and then I do the estimation. And depending on how much noise there is in this design matrix or the strengths of the correlations, that two-stage approach could be simpler and faster and extremely effective, or it could be more sensitive to noise and have some challenges. So it really depends on the setting. Right. Okay, and so here, instead of just showing you some toy examples, I'm showing plots of the mean squared error, or the log mean squared error, as a function of n, so how many different samples or stimuli we're presenting to our fMRI patient. And here I'm looking at the log mean squared error versus R, which is the strength of those correlations among different covariates. And so the red lines correspond to cluster representative lasso, blue lines to the graph total variation, green is regular lasso, and as we would expect, it's terrible. And OWL, which never takes in any kind of side information, is, I think, doing very well under those circumstances. Okay, so let's look at sort of the other extreme, a chain graph. So our sigma matrix would look like this. Well, it would look like this. So we've got a strong diagonal and then two strong off diagonals. And again, what we can do is we can look at the mean squared error of the graph total variation estimator and the mean squared error of the lasso. And what we see is that we can get an extra factor of p in the denominator by using this total variation that we're not able to get with a classical lasso estimator. Now, in contrast to this sort of block diagonal sigma matrix that we looked at in the last example, here there's no clear clusters. So if I was going to try to find groups of covariates to cluster, it's really unclear without any additional information about where to draw those dividing lines. And what we see in simulations is that if we try to do some clustering, either we end up with p different clusters, each of size 1, or one giant cluster. So in this simulation, what we did is we did have a full chain graph, but we said beta is really only active on a small segment within that graph, and here I'm showing that. And so again, here are the estimates with the graph total variation, which really outperform the lasso. And what we see is that, again, with the cluster representative lasso, we're having a little bit of a challenge because it's difficult to do that clustering in this case because there aren't really strong clusters. Whereas in our situation, we're again using the information in our responses y to figure out where this sort of breakpoint between active and inactive should be and to implicitly do the clustering in a way that's adaptive to our response variables. Okay, so again, here is the log mean squared error as a function of p, the number of different covariates we have, or as a function of r. And our graph total variation stuff is scaling the way our theory would more or less suggest, but we're also seeing that we have a strong empirical performance relative to other methods in these situations. And that the strengths of different methods really depend on how strong these different correlations are.
This is the mean squared error on the level of the betas, not on the predicted values.
That's right. We're looking at the mean squared errors of the betas. So we're really focusing on model selection error as opposed to prediction error. I think you might need less machinery to just get good prediction error here. Okay, so at the very beginning, I told you about this neural decoding problem. And so what we did is we worked with some collaborators at the University of Wisconsin to actually try this out on some real fMRI data. And this is very much still work in progress, so I just have some preliminary results that I can show you. But there's a lab at Wisconsin headed by Brad Postel that collected what he calls the faces, places, and objects data. So it's very much what I described earlier. You've got subjects sitting in the scanner or laying down in the scanner and looking at pictures of either faces or places or objects. And we said, how well can we figure out how people encode whether they're looking at a face or something that's not a face. To estimate this covariance matrix sigma, what we used is the full time series of observations. So what I mentioned earlier is that with fMRI, I measure the bold or blood oxygenation level dependent signal over time, and then I just fit a parameter to it to populate my design matrix X. But so I end up throwing away a lot of information in the original fMRI data. In order to estimate this sigma covariance matrix, I'm actually pulling that data back out and using the full time series to get more accurate estimates of this covariance structure. So it's not as far as we want to go, where we ultimately like to find a data set where we're using diffusion MRI to estimate sigma, but this is a good first step proxy. And then all the parameters for all the methods that we looked at were set via cross-validation. And so what I'm showing here is prediction error. We can't really measure model selection error for the real data. But out of 30 different trials, so I've got 10 different subjects, and we analyzed each of them independently. And for each one, there were 30 different trials in our test set after doing our training. And we're looking at the holdout accuracy among those trials. And so what we're seeing is across the board, this graph total variation and the OWL are both doing well. Graph total variation seems to be doing slightly better in a number of different subjects. And here I have a visualization that was generated by the psychologists that I work with at the University of Wisconsin, Chris Cox and Tim Rogers, who generated it for some different data sets, or for some different estimators than what I've talked about so far. So first of all, they said, okay, just based on current psychological models of the brain, these are the regions in red that we think are encoding information about faces, and in blue are the regions that we think are encoding information about places. But these are hypotheses, and it's far from certain. And in fact, there's a big debate within that community about whether the encodings of these things are highly localized in small regions of interest or rather distributed across large swaths of the brain. And that's one of the things that they'd like to use these methods to somehow infer. So now what we could do is we could run the lasso for each of the 10 subjects, and then we're coloring in a voxel if a voxel is considered active for at least half of the patients. And then we are coloring it depending on whether it's somehow positive for encoding faces or negative for encoding faces, like whether it's getting a positive or a negative weight. The graph total variation approach that I've been describing all day today results in much more diffuse and spread out measurements where, and so this again is showing where we've got 50% of the subjects or more using that voxel to encode information. And this is exactly what you would expect, and because we are not enforcing as much sparsity as the lasso estimator. But what's interesting is that the support of this estimate seems to be similar to the support of something called the SOS lasso. It was also developed by Rob Nowak, and it was a method to somehow jointly estimate encodings based on all of the subjects simultaneously without mapping them to a common template. And so when we start thinking about, well, what's going on across multiple subjects, it seems like there's some support from multiple different perspectives that are based on very different assumptions, for this sort of broader and more distributed encoding of this information. Okay, but like I said, that's very preliminary. So right now we're working in more detail with these psychologists to really test this out more rigorously and to validate these results more carefully. But overall, I think what we've seen is that by using this underlying graph structure, what we are doing is getting a mechanism for doing regularization and at the same time account for strongly correlated covariates in these estimation problems. So it seems like there's some potential here both from a theoretical perspective and in practice, though I think we need much more thorough evaluations on real data, and that's one of the things we're working on now. We're also exploring the specifics of these performance bounds for more graph structures beyond this block complete or chain graph that I think will be very interesting. And then we're also looking at some computational and optimization speed-ups for very large, very dense graphs. Okay, well with that, thank you very much. Let me just say one other thing. We posted the paper for this to archive yesterday, but I don't yet have the number to show you, but it should be appearing later today. And if you can't find it, send me an email and I'd be happy to send it to you. Okay, thank you very much.
I'm sure many of us are recovering from Richard and not liking puppies, so that's level thinking. Questions?
You tried to solve an inverse problem in the first place. So that's why you really need to regularize the design matrix, right? I didn't see this showing up in your analysis. I mean, I understand that the part that regularizes, I guess that is the answer on my question, that the Laplacian smoothing part. Is it important because you have an inverse problem to solve? Is that correct? If you hadn't had that, maybe you could kind of put this a little bit aside.
So the design matrix is what it is. So we don't regularize it, but we do some regularization to account for bad behavior in the design matrix. So when you look at these bounds, I guess I didn't really emphasize this enough. This denominator corresponds to what we would think of as the restricted eigenvalue constant in other literature. The issue is that when you have highly correlated columns, then the minimum eigenvalue of sigma alone, without this here, could be arbitrarily close to 0, making these bounds very bad. And so by adding in this Laplacian smoothing term, we offset that. And so this is always bounded away from 0 as long as lambda s is bounded away from 0. And so we're able to sort of mitigate the problems associated with the ill-posedness of x.
And so I was wrong. I thought that the total variation penalty would also help to regularize this minimum eigenvalue. And this is not true?
Yeah, I mean, it's a good question, and it's something that we thought about. I mean, when you look at this regularizer here, I mean, yeah, these two terms on one hand seem similar. In the theory, they certainly seem to play different roles. And when we do our estimation, setting either to 0 doesn't work as well as having non-zero values for both lambda s and this lambda tv. But at the same time, it's not clear to what extent both are strictly necessary and to what extent it's an artifact of our analysis techniques. But what I would say is that when you look at something like the elastic net has one regularization that's the 2 norm squared of beta and another term that's the 1 norm of beta. And both play important roles. It's not like you can really do with one and not the other and get the same kind of performance. And so I suspect that there really is something similar going on here, where they are playing different roles and both are important and significant. But I also think that our understanding is not totally complete there.
Thank you.
So I was wondering, how did you choose all these regularization parameters?
Cross-validation. Yeah.
That's
So
actually very time-consuming.
it is. So for instance, with this fMRI data set, we, for each patient, had 100 different scans. 30 we held out as a holdout data set. And then on the remaining 70, we did, I think, 5-fold cross-validation. And then we did that for all 10 subjects. And yeah, it took some time. But, I mean, I don't know of a better way to do it.
So, I was just curious, one of these things that people sort of seem to complain about with lasso is that it takes too many variables, or at least this is what I hear every once in a while. So if you use this thing on something where the correlation between the x's has no relation to the betas, or very minimal, how does it compare to lasso? In this case, does it still take a lot of variables, or does it?
Yeah, I would just say it's a different problem. So yes, it will. For any of these methods, I'm lost in my slides here. Let's see. So let's look at the fused lasso, which is maybe the most widely known, where you've got 2 regularizers. One is measuring some measure of the pairwise differences of beta according to some graph encapsulated in D, and then I've got a lasso term as well. And there D has no real relation to the structure in X, which is exactly what you're talking about. So there, because I want to have lots of pairwise differences of the betas being close to 0, I'm naturally going to have more non-zero betas. And so, I mean, if you really want an extremely sparse beta vector, then none of these methods are for you.
But this is something that...
I mean, I think to some extent it's application dependent, right? There's some settings where you really do want the very sparsest possible beta, but I would argue that there are many applications where that's not reasonable. Like, for instance, in this fMRI case, yeah, I could come up with the sparsest possible beta for this decoding problem, but whether that's really real or whether I'm just fitting to noise, well, I'm pretty sure you're just fitting to noise. And so, yeah, you could get nice sparse estimates, but I don't really think it's going to be something that's repeatable with any kind of consistency. So I don't think that that's the right sort of metric for those sorts of problems. So yeah, none of these things are going to give you estimates that are as sparse as classical lasso or other things like, that are even sparser.
Just a comment, if you're concerned about this, you can always change your sparsity penalty. You can replace lasso by any variant which does a better job without giving up the other 2 nice elements. Maybe you cannot do the same theory, but if you're really concerned about working on the properties of your beta being less sparse or more biased or less biased, I guess there are very many variants to replace the classical lasso. Yeah,
this is a pretty sparse literature review. In the paper we talk about another method based on MCP, model maximum concave penalty or something like that, where you no longer have a convex optimization problem, but you can get less bias and perhaps sparser estimates. So yeah, there are definitely things like that out there, but if you think doing cross-validation is slow, then trying to do many random restarts to handle non-convex estimators, that's going to be slower.
Last question, Dave.
It was kind of dual to Holger's question, which is, since there are several tuning parameters, I mean, how stable are the results to sort of varying these parameters? Are there trade-offs between them in terms of what's going on? So there's one question is, how do you sort of choose them in a cross-validation setting? The other is, how can you break this in terms of playing around with the tuning parameters? What are the instabilities one might expect?
Right. Well, so if you were to just ask, can I do small little tweaks to these different parameters, lambda 1, lambda TV, lambda S, will it give me dramatically different results? That's a great question, something that we have not looked at carefully. But if you were to start sending some of these things to 0, like lambda S, then things could, yeah.
Certainly not. I was just wondering in terms of, how strongly, since there are it's already bad enough sometimes when there's 1.
Right. Yeah, it's a very good question, and we have not looked at that yet. Yeah.
Okay, let's thank
Thank you very
Becca
much.
for a great talk.